Right. Hello, everyone. It's my great pleasure to introduce Professor Walid Saad, who received his PhD degree from University of Oslo, Norway, in 2010. He's currently a professor at Virginia Tech's Electrical and Computer Engineering Department, where he leads the Network Science, Wireless, and Security News Group. He's also the NextG Wireless Faculty Lead at Virginia Tech's Innovation Campus. His research interests include wireless network, 5G, 6G, and beyond, machine learning, game theory, security, UAVs, semantic communication, cyber-physical systems, and network science. Dr. Saad is a fellow of the IEEE. He is also the recipient of the NSF Career Award in 2013 and the Young Investigator Award from the Office of Naval Research in 2015. He was the author or co-author of 11 Conference Best Paper Awards, including IEEE Smart Gridcom and IEEE GLOCom. His research was recognized with the prestigious IEEE Fred W. Millersick Prize from the IEEE Communication Society in 2015 and 2022. He was also a co-author of papers that received the 2019 and 2021 IEEE Communication Society Young Author Best Paper Award. Other recognitions include 2017 IEEE ComSoc Best Young Professional in Academia Award, 2018 IEEE ComSoc Radio Communications Committee Early Achievement Award, and the 2019 IEEE ComSoc Communication Theory Technical Committee Early Achievement Award. He has been annually listed in the Clarivate Web of Science Highly Cited Researchers list since 2019. Dr. Saad is currently the editor-in-chief of the IEEE Transactions and Machine Learning in Communications and Networking. Thank you, Professor Saad, for accepting our invitation. The floor is yours.
Thank you so much. So sorry, I also got the Zoom just crashed, which is why I went out and in. So today's talk, it's a great pleasure to give this talk. And thank you, Handy, for the invitation. So in today's talk, I'm gonna go a little bit into the relationship between artificial intelligence and wireless communications, and how these two techniques became a little bit closer to each other over the years. So a little bit of the outline. I'll start with the evolution of wireless, and I'll talk about two parts. The first is maybe more on how do you create networks that support AI, and particularly federated learning. And the second part is how do you use AI to improve wireless networks, and I'll talk about different things across the two areas. So in terms of like a brief evolution of wireless and AI and how they were, just first in terms of wireless, 4G was one of the major cellular systems of the past decade, or LTE, and we still use it today. And it's focused primarily on data rate and multimedia, right? And today we started to have 5G, where we focus more. We still have data rate as an important thing, right? We need to have gigabits per second, but we also need to have reliability and latency. And a key application is the Internet of Things. Tomorrow in 6G, we want to have probably all three together, like data rate, low latency, and high reliability. And this would be an enabler for holographic society. We could potentially be able to do this talk while I'm holographically teleported to Miami, and we can even interact kind of virtually. But what was the perspective of the wireless community, which I'm a part of, on AI over these years? So on 4G, AI was shunned. So whenever I used to present about AI, people would say, oh, this will never fly, it doesn't work, for wireless, we don't need it. In 5G, they were using it now as, they tolerate AI in some sense. So they were using it to tweak protocols, so improve some of the wireless protocols and make sure that, we can use some autonomy in that. And in the future, they're starting to love AI, and a lot of companies, standardization bodies are starting to think on how we create AI native wireless networks, which are wireless networks where AI plays a major role across many protocols. It's not the only tool there, but it plays a significant role. So the relationship has been tense and complicated over the years, but it went from a hate to a love relationship, which we hope will continue over the next few years as well. So in this space, we can divide the two, the research activities into two areas. The first one is, how do you design the network to support AI tasks and operations? And federated learning is an important use case. I'll get to it in a moment. And I know Hadi and probably most of you are more experts in federated learning than me as well. So there's an intertwining between AI and wireless here. And the question is, how do I prepare the network to support federated learning and others, right? AI algorithms running over that. The second area, which is the more traditional one for us in communication, is how to use AI to improve the network, right? So how do you use AI to do resource allocation, to do optimization of the network and so on. And here we're gonna, we can distinguish three use cases. One is data analytics, where you just use the information to kind of come up with, let's say, a map of the network. Second is optimization, and I'll talk about that later. And a big tool there is reinforcement learning. And the third use case is edge AI, whether you use federated learning or other tools to optimize communications. Now, of course, the question we've been asking, and we'll soon have a paper more on this, is which AI do we need for 6G and even beyond that, right? So what are the features of AI that we need to create AI native wireless networks? And we identified 6 features. The first one is explainable, right? So we need, in wireless, it's necessary to have some sort of performance guarantees. We cannot just throw in black boxes all the time and just hope they perform the way we want them to. Second is, on the right-hand side, distributed and collective, right? Distributed in the sense of you do not need to rely always on a central server, or at least it could be federated. Or you can eventually become like a collective brain power, right? Swarm of AI tools that would create and operate the network. And third is reasoning based, which means that you can now, instead of only doing statistical analysis to your data, you can understand the causal and associational logic behind that data and make conclusions out of that data. This comes hand in hand with generalizability, because we need to have AI models, at least for wireless, that have generalizable and transferable skills in the sense that they can quickly adapt to unseen environments. And it has to be lifelong in the sense that they can continually learn from the data. And a very important area, in my opinion, related to AI and wireless together is green and sustainability. In other words, what are the energy efficiency or even the power consumption bills for AI and wireless? And I know at FIU you have quite a bit of work on smart grids, renewable energy, but how we connect that to the use of AI in a network would be an interesting area. In today's talk, I'm going to talk about distributed, collective, and green in the first part in the network for AI. And I'm going to talk about reasoning-based and generalizable in the AI for networks. Now, I'll start with the right-hand side. I'll start with federated learning and its use over networks. I know that you know quite a bit of federated learning, so a quick introduction. It has been a topic of massive interest in both the AI and system networking communities. But the focus has been primarily on designing algorithms, right? So you need Fed averaging, Fed procs, and all sorts of abbreviations you can come up with federated learning, right? So there's all these algorithmic designs. But most of them assume abundant wireless resources, or they assume that the wireless network is just a bandwidth, right? Which is a good assumption if you're working, let's say, with Wi-Fi or some other limited geographically limited wireless networks. But if you're going to use a real network like 5G, then it's not just a bandwidth thing, right? I mean, wireless resources have a strong impact on the federated learning algorithm, and we wanted to understand that impact on federated learning. And this was kind of the first problem we tackled in this space, and I'll talk about it a bit more in a moment. Now, the other assumption that has been in kind of most of the works on federated learning is that the devices can run complex neural networks, and complex in the sense of difficult, not complex numbers. So like devices, for example, Amazon's Home Assistants, they have very strict memory, computing, and energy constraints. So how do we tailor federated learning to work on these resource-constrained devices? And that's the second problem we've been looking at. And directly related to that is the carbon footprint, right, or the energy efficiency. So how do you create green FL or green AI in the general sense? So this is a work. The first part has been part of a series of works we've done before, currently supported by an NSF project. But these two are more related to a project by Amazon, where they wanted us to actually look at how FL can work on their home assistants, actually, and take into account these memory constraints. And problem 4, which I'm not going to talk about today, is more about scalability. How do you scale FL with many devices, right? And there are questions of game theory and other things that come into play. So let's focus on problem 1 today, and I'll give you a flavor on problems 2 and 3 just briefly. So the first work, I mean, this is from one of the earliest and perhaps the first work that really thought about communication as a means to support federated learning. And we called it at the time joint learning and communication. And I'll tell you in a moment why that makes sense. So The system model is the following. We have a federated learning algorithm. Assume it for now, it's federated averaging, but we extended that to others. And it's trying to exchange, they're trying to exchange the weights with the base station, a cellular base station. And of course, there's the aggregation there, and the base station will send back the global model to the devices. So it's a very classic federated learning model. But the key point for us here was that these links are not perfect. So you have wireless impediments, including interference from other devices, including a fading of the channel, like Rayleigh fading and shadowing, including bit errors, right? So how do we actually account for those when designing the learning algorithm? So we wanted to come up with a real-world model for the wireless that can support FL and understand how do these wireless impediments impact federated learning, if any, if they do impact it, right? So that's something I mean, that's a question that we answered, and the answer, of course, is yes. So the process, the way it works, it's a classical FL, but just putting it into the context of wireless. So the base station will send the global models, and then the users do their local updates. And then they transmit their local model to the base station over the uplink of the wireless network. It updates that model, and then we look at convergence and so on. So we have transmission errors impacting the federated learning performance in the uplink. For downlink, we only take into account delay, and we take into account energy consumption in both uplink and downlink. Okay, so these are the main metrics we'll take into account. So modeling a little bit. So the uplink rate, I know some of you may not be in the wireless domain. So this is the classical Shannon rate. So we have the resource allocation vectors, how many resource blocks. So in 5G, a resource block is if you want, you can think about it as a time frequency chunk that we give to a user. So we're trying to optimize that here. And we have the transmit power, the channel, and HI. I mean, HI is the channel, I don't have the bullet for it. HI is the channel, B is the bandwidth in the uplink, N is the noise, I is interference from other base station, other devices in this case. And R, again, it's a 0-1 resource block allocation vector. Capital R is the number of resource blocks you have. So this is uplink, meaning from the device to the base station. For the downlink, we have a similar expression from the base station to the device. And then the first exposure on where FL and wireless come into play comes in these equations at the bottom. So this is the delay in the uplink. Again, function of Ri, the resource allocation block, Pi, the power. But it's also function of the data size of your weights and of the uplink rate. So you can see in this very simple initial example, equation, the wireless in the denominator is related to the FL in the denominator, in the numerator. And similarly for downlink. So this is uplink, this is downlink. Okay. So now I have these delays and I have the data size of L. I can actually also model the transmission error. So we assume a coded channel with a packet error rate QIN for a given resource block. And QIN is 1 minus the exponent. This is a well-known bit error rate or packet error rate, sorry, equation. So it's a classical one. But what we do here, now where FL comes into play, we say that, let me show you the whole slide. You have this CWI, which you can think about it as an indicator function. This depends on the bit error rate. If the bit error rate is high, then I will not use that weight in my FL update because that weight is an error. So it will not be useful. So we kind of eliminate, prune, if you want, these weights, we don't use them. And then we do the global aggregation. But you can see now that G is function of P, power, R resource block, and A is whether the device will transmit or not. So it's an indicator function as well. Okay, so this shows you how wireless and FL come into play, which allows us to pose the problem more formally. So the problem here is we're trying to find the wireless parameters A, P, and R. Again, R and A are just indicators to allocate a user and allocate a resource block to that user. P is the power. And we're trying to minimize the loss function. So this is federated learning metric, right? F is a federated learning metric. APR are wireless metrics. XI and YI are just the data samples. KI is the number of samples per user I. U is the number of users in the network. Okay, so this is I. Now the constraints, this is just feasibility, the first one. But the key one is we have a delay, total delay constraint. So the total up and down should be constrained by gamma. And we have an energy constraint as well here, which is also constrained by a gamma E for energy. These are just feasibility constraints. So the power is positive, it's below 3 max, and the RI, you cannot allocate more than one resource block per user. Now, the question is, can we solve this problem? Turns out that to solve this problem, we need to initially understand the convergence of federated learning. And this led to the literally the first proof that shows how FL and wireless are intertwined. You can see from this convergence proof, where we're trying to find, the convergence of the federated learning loss to an optimal solution, G star, so the global model. You can see that this is bounded by these two terms. If you don't have wireless, if you assume wireless is quote unquote a bit pipe that is errorless, this term does not exist. You only have this second term. A is a number between 0 and 1. It's a constant, and between 0 and 1. If t goes to infinity, then this goes to 0. Clearly, then the FL will converge. But if t goes to infinity, this term does not go to 0. And this term, while it depends on many parameters, the key one is QI. QI is the packet error rate. So this shows explicitly, that the convergence of federated learning is not necessarily guaranteed over a wireless network unless your packet error rate is low enough, right? So unless unless this term is small. And this says that the wireless network must be reliable enough to support a practical federated learning. This proof is for full gradient descent. You can do it for stochastic. We did it actually. It's not very hard. But this is, I wanted to show you the early on result. Now, it turns out to solve the problem I had on the previous slide, given this proof, you only need to minimize this term, and which gives us an easy way to solve the optimization problem. So we can find the optimal power first, and it's just, it's just the power that satisfies this inequality. It's very easy to find. And second, to do the allocation, we use the Hungarian method. Okay, so the merit of this work was not in the optimization part, which is very classical. It's more in the showing how this wireless and federated learning are intertwined. And this tells you here, it's a very completely different view of learning, that we actually changed the community's perspective in this field, where we're optimizing the network to serve the FL, as opposed to most of the works in wireless, which are AI for networks, right? Not networks for AI. Now, a few simulation results. So you can see here the identification accuracy versus time. We compared to 3 baselines. Baseline C, let's forget a bit about it. That was like a very random baseline. It always performs poorly. Baseline A is our algorithm without the optimization, and without the optimization of the resource blocks. And baseline B is Google's classical federated averaging, which assumes the wireless is ideal. You can see we are significantly better compared to baseline B, and also compared to baseline A. And this also scales well with the number of users. So we can see our proposed algorithm has a higher accuracy, and it scales with the number of users as well. Okay, so this corroborates that. Now, what about the energy and resource constraints that I talked about early on? How do we account for this? So in a more recent work, using somewhat the same perspective, if you want, but now instead of using a CNN or a complex neural network, we use a quantized neural network. And there's two types of quantization we do here. The first one is quantizing the weights. So D is a quantized version of W that I showed before, but that was something that people have proposed before us, actually. So we just used that. But what we also propose is to fit on small devices, we need to quantize the neural network. While quantized neural networks have been around for a while, their use in federated learning was kind of limited. And in this work, we kind of started to see, can we use them? And this brought interesting trade-offs, because now you want to minimize energy, which means you want to quantize. But you also want to maximize accuracy, which means you don't want to quantize, right? So there's a trade-off between these two different goals, if you want. And at the same time, you need to maintain a low or low latency or a quick convergence time. That is also affected by whether you quantize or not. So there's a trade-off that comes into play here. And the question for us was, of course, a convergence question. We had to answer that. But the question was also, can we tweak the quantization levels, both for the neural network and for the quantization over the channel? And can we pick the number of devices, so which devices to transmit, in a way to kind of minimize energy efficiency, but not jeopardize the accuracy of the network? So the first theorem we had is another convergence theorem, if you want, but this is with quantization, which is a little bit harder to do than the one previously. So we can show that for a given learning rate, there are various parameters here, but I'm going to just give you the insights across. So for the learning rate at tau, which is function of these beta and rho, which again, they are constant in this case. And what we call the degree of non-IEDness, right? The difference between different samples for a given device, which is something we just defined as this metric. We have this convergence here, which is bounded by this term, where these values psi1, psi2 are defined here. So here what do you have? What is that function of? It's function of small n, which is the precision level, how much quantization I'm doing at the level of the device. It's also a function of m, which is the number of bits to quantize for transmission. It's dependent on the sampling probability. With what probability do I pick k users? And it's dependent on the variance of the gradient descent. What's interesting here is that as these precision levels increase, you have a better convergence rate, but unfortunately you pay more energy. And also I, which are the number of local iterations, you can see it here, and k, the number of devices I pick, also impact convergence. So the convergence rate is complex in the sense that it depends on how much you quantize, both at the level of the neural network and at the level of the wireless, and how many local iterations do you do, and how many devices do you pick. So this is a very fundamental kind of perspective on this. And with that, we can actually pose an optimization problem as usual. It's a dual objective optimization problem. We wanted to minimize the energy, and this includes the energy to transmit, the uplink, and also the energy to compute, so the energy you need on the device itself. So we have models for both. The model for the first one is similar to what I presented early on. The model for the second one, there was a paper that looked at the energy needed to perform neural networks. It's a hardware paper, not in my field, but they had some nice results that gave us expressions for this term. So this is the total energy consumption over time t. T is the convergence rate or the convergence time. So we want to minimize the convergence time, but also minimize energy. And these two are not in a line. They're conflicting. Now here we have constraints on I, so it's between a min and a max, k between a minimum number of devices and the maximum total, m as well. And this is the accuracy constraint, right? So I need to make sure that I still am accurate in my prediction. So again, these are number quantification rounds, energy consumption for local training and uplink communication. And the local training is the one that includes computing. I is the number of local training, k is the number of selected devices. As I said, n and n are the precision levels. One is for communication, one is for local training, and this is the accuracy constraint. After t rounds, how accurate is my federated learning? Now it turns out that to solve this problem, you need to find Pareto optimal points, right? So we use a classical technique called the normal boundary inspection to find the Pareto optimal boundary. But once you have the Pareto optimal boundary, the question is, which point do you pick on that boundary? So we investigate two of them, one which minimizes the sum, and one which is for those of you familiar with game theory, is the so-called Nash bargaining solution. And Nash bargaining solution is known to be Pareto optimal and quote unquote fair point that you can pick on a Pareto optimal boundary in an optimization problem. So with that said, some simulation results. So on the left-hand side, I show energy in black, communication rounds in red, accuracy in the x-axis. You need very low accuracy. You need to spend the joules and the communication rounds needed for that to happen. You decrease your accuracy constraint, then you need very few rounds and very little energy. Of course, having a 10% accuracy is not great. So something in here may be where you should operate. And this tells you how your system should operate. You can see that the Nash bargaining solution, which we advocated for, is in square. It gives you less energy, less communication round across. So you can see the square is better than the star. The star just minimizes the sum. And in that case, you may end up having higher energy and maybe even higher communication rounds. Okay, and on the right-hand side, I show the precision level, the target accuracy, where you have in blue, the one that only cares about energy, in black, the one that only cares about convergence rate, in red, Nash bargaining solution, in green, the sum rate. You can see that the precision we need is close to actually the sum rate in this case, and it's much smaller than what the convergence round minimizing one needs. In fact, if you want to only minimize the convergence round, you use full precision. You don't do quantization, and it's of course higher than what you would need to minimize energy, and that makes sense. We're trading off. Now, if you're interested more in FL, so I'm not going to talk too much more about it today. In one of our works, we looked at how you do federated learning for generative networks. And that's something that at the time had a lot of applications. But now with large language models, I think this GAN-based distributed GAN, which we did, would have quite a few interesting applications. At the time, we looked at it for UAV networks. We looked also at convergence time, a focused version of the work, and this we got the best paper award at ICC a couple of years back. And then we looked at fully distributed no base station approaches, more like economics approaches as well, using FL to do optimization as well in wireless. And most recently, we looked at control communication in FL with drones and vehicles, and also urban air mobility. So this includes an ICC paper, TWC last year, and another one accepted actually last week, which looks at urban air mobility. So this area is ripe of interesting problems that you can do. Now, I'm going to flip the coin now and go to the AI for networks section and spend maybe the same amount of time there. So first, the classical works in the AI for networks literature, usually for us as wireless engineers, the easiest way to use AI was to use reinforcement learning. But reinforcement learning has some issues. And one of them is that it's not quick and it's not very generalizable. So we kind of propose this idea of experience deep RL, which also uses GANs for improving reliable communication. So if you look at 5G, there is a type of traffic called ultra reliable low latency communication, or URLLC. URLLC was proposed to support Internet of Things type of communication, where you send short packets in the uplink to a base station, and that base station will process those sensing results. The idea is that you need to have the link significantly reliable, meaning the error rate very, very low. And usually we talk about 5.9 reliability, which means 99.999% of the time you need to arrive correctly, you bid to arrive correctly, and low latency. But unfortunately, in the classical URLC paradigm, while it's effective for these IoT scenarios, in 6G, it has to be different and it has to go a little bit more extreme. On the one hand, it's not necessarily uplink anymore because drones and vehicles, they need downlink sensors. And it's not necessarily small packets, it could be large packets. Also, classical works assume that you know the model for the traffic, but latency is hard to model, especially in a wireless end-to-end link. So can we use model-free approaches? Some people thought of that, and they said, okay, we'll do model-free deep RL. But deep RL is slow, and it's not really reliable when it sees unseen conditions. It can adapt to them, but it takes time. So deep RL for URLLC, while it was an interesting area, it's a bit contradictory because you want reliable low latency, and you plug in deep RL, which is not reliable and not low latency. And how do you achieve the two? And that's the question we try to answer here. Can we design a reliable deep RL or reliable AI in general that works well under extreme conditions, meaning a deep fade, a blockage of your link, to achieve URLLC, or more broadly, just to achieve reliable links? So the problem formulation here, I'll keep it simple and kind of like straight to the point. We're trying to minimize the power we're allocating to users. So it's a single base station downlink, single base station, multiple users. I'm trying to allocate resource blocks. So this row indicates resource blocks with a minimal power. You have K users, you have N users, K resource blocks, and T is time. I have multiple conditions or multiple constraints here. The key one is the first one. I need to maintain the delay below the max for significantly large portion of it. So this is the actually this is the reverse of the reliability here. I want to make sure that DI does not exceed DI max more than 1 minus gamma I star, which means gamma I star is my reliability. I need the rate to be, I mean, there are feasibility constraints here, and I have a rate constraint. So I need the rate to be greater than a certain value to make sure that the delay is low as well. So, but the challenging part here is twofold. One, I don't assume any model for the delay. So DI, I don't have a mathematical model for it. DI max is a constant. And second is this constraint. If you have a model for DI, some of our previous work and by others as well, we can convert this constraint and use, if you're familiar with Lyapunov optimization, and we can solve this problem. But when you say it's a model-free problem, these constraints cannot be converted, and then Lyapunov cannot be used. So you need to do learning, right? It's obvious. So we need to do the DeepRL because it's appropriate. It can handle large state spaces, but there are challenges. So the challenges are twofold here. One is important, but a challenge that we solve kind of in an easy way. And second is a second challenge, which is more prominent. The first one is we also have a large action space. So to solve that, what we did is our DeepRL framework starts with a PPO algorithm, the well-known proximal policy optimization algorithm. And instead of optimizing power and resource blocks, we find the rate. And then we plug that into what's something that we unoriginally called action space reducer. It's an optimization problem which reduces the action space. It's a heuristic, but we show that this makes it polynomial in time. And we can also show that after convergence, we actually guarantee reliability for the user. So this is all good things, but the key question we don't answer yet is DeepRL is not reliable because it's slow to converge. And when there are extreme cases, which means, again, fading of the channel that you didn't see before, or a blockage or a certain user coming up with new interference, you're very slow and unreliable in phase 2 of that. So how do we solve that? We use generative networks. And this is how we do it. So one idea to improve DeepRL that we have advocated for, and a lot of people have done as well, which is to train the DeepRL agent offline. But there's a problem with that when it comes to wireless. One is we don't have data on wireless. If you're working in this area, you know that operators don't share the data, and the data available online is often limited in what you can. So how do we create a virtual offline environment that actually is can have real data, but it's limited, but also synthetic data that we can control? This is where we use GAN. Now, after you do this offline training, you can deploy your DeepRL agent in the network, and it works. So on the left-hand side, it's an offline training. On the right-hand side is the actual deployment. So how do we solve this virtual environment? How do we design it? We actually use something called a GAN-based design. So it turns out that in 2015, actually, Apple was looking at a problem that's a bit similar to ours, but it doesn't have optimization or DeepRL. They had this problem. They had unlabeled images of eyes looking in different directions. And they had a very actually well-designed simulator that generates synthetic photos of eyes. And they wanted to use the limited unlabeled images with the synthetic controllable network to actually find eyes of different types of eyes, right? Different style, different directions looking, and things of that sort. So they proposed this refiner GAN, which takes as input two things: unlabeled real images, synthetic images, and refines them into, real-like images. So we use the same. For us, what we say is, as I already mentioned, we have unlabeled real information from a network. In this paper, we use packet arrivals, so what is the arrival rate, and channel information from a data set available online. And we had a synthetic data set where we can use models actually to generate all sorts of synthetic data. We plug those into a refiner, and then now we have refined channel in packet arrival that's controllable because I can control this, and that allows me to actually be compliant to this scarce but available real data. And we use this to train the DeepRL agent. So in Apple's work, they just generate this. Here we use this to train the DeepRL agent. The output would be a experienced DeepRL because now he's gaining experience here. And because I can control this, I can actually generate some extreme points, which means when I deploy the DeepRL agents, he would have seen a bigger experience before being deployed, which means he will be more reliable, and we can show that in the simulation. So first, we show the convergence time. We compare with three things: DeepRL without offline training, DeepRL in blue, DeepRL trained with only real data, in green, DeepRL trained with only synthetic data, and in red is our experience RL. You can see that they all converge to the same point, which makes sense at the end of it. But what we're interested in is this transient period. In this transient period, you can see that synthetically pre-trained and vanilla DeepRL are very slow. They need 50 epochs to get to a point that's close to optimal. Or I don't want to say optimal, but close to the solution we find. The blue is a bit better. So synthetically pre-trained with real data is a bit better, but clearly ours is extremely fast. So it quickly gets to your point. Now, what we also did is at epoch 100, I believe, we inserted we kind of shot an extreme event, like the traffic arrival increased significantly. What happens in this case? You can see that all four algorithms will adapt. Vanilla DeepRL takes 100 epoch to adapt, and also synthetic and pre-trained with real data, they take about 50 epoch to adapt. You can see that ours adapts almost immediately. And this is what we're looking at, right? So we're trying to slash the convergence speed of RL when it's deployed in these environments where it sees it's. I mean, this shows reliability at the end of the day. This is showing we are more reliable to these extreme events. Now, moving on, I mean, this is a bit generalizable, but not much so. So what can we do more with this? So some open questions. I mean, one way is to explore what we call disentangled representations. So pieces of data that you can synthesize in the way you want. And there are other areas we can look at. So we have a multi-agent and more generalizable RL work than this one. We applied it to drone using Meta RL. You can see my work with my former student here, and she's done quite significant work in this space and was one of the first to actually look at this. And then can we have a multi-agent GAN? I mentioned that before. And can we use distributions, not averages? So instead of optimizing the expectation of the reward, we can look at the distribution of the reward. And we did that with my former student as well, Chin Chin Dang. And we also looked at deep array architectures with better ANN. So here I use DQ, but you can use like a deep LSTM or a deep echo state network and things like that. Now, the next question for me, which is the last part of my presentation, is can we go from this experience-based but data-driven approach towards what I called AI native and more interestingly, knowledge-driven reasoning? And I'll kind of try to give you some insights there. I think I still have a bit of time to do that. So this is based on a series of papers, very recent papers on this area of semantic communication, but more broadly on this philosophy of less data, more knowledge. So if you think about wireless and data analytics, they have been tied together for decades. Early work was what I call data-driven, which means that I kind of, let's say, find the quality of service based on the data. But this is not very intelligent, right? I mean, we need to do more with the data. Today's network, in my opinion, are here. They're information-driven, where I link some elements in the data, like the pink ones are linked or the purple, and the green ones are linked. And this allows me to create metrics like age of information, like information-centric networks, right? So here, it's like application-aware networks. Now, the next steps are these two. We need to come up with a way to connect the dots and create a knowledge map. I know that this information is related to this. This device is related to this. This point of this application is related to this. This allows us to have organized information, not just information, but organized information. And this is where we use things like meta-learning and things like that. And this is where generalizability comes into play, because now if I have a knowledge map and I see a point here, I can make a connection and say, okay, I can generalize to this point. A step further would be to get to reasoning, where I actually understand what are the logic propositions that tie my data, what are the associations between these data points, and how do I actually extract this information using primarily causality and what we call neuro-symbolic AI that I will talk about. Now, to get to this, you need to change your perspective on what the transmitter and receiver are doing. And you need to make them what we like to call at least now, teacher apprentice. And I'll tell you what that is. So classical wireless looks like this, right? You have a transmitter, you encode the bits, you send them to a base station or over the cloud, you get to another base station, and then the receiver decodes those bits. And because of Shannon's paper in 1948, the bits, the transmitter and receiver are not aware of the bits. They don't know what's inside those bits. They assume it's just ones and zeros. They can do a lot of things like joint source coding, like you can even use AI to do modulation and things like that, but I don't know what's inside those. And this has been a good design. And the proof is you can communicate today. I mean, everything we do today is based on this design. But we think that this is not enough for future applications, like the metaverse, like collaborative robotics, because in that case, the meaning of the messages, which we call semantics, may play a role in how you send data. So instead of sending all the bits, the idea of so-called semantic communication says that I can take the bits, represent them using meaning. So I find meaning in the bits, and then I only send the meaning, and I rely on the apprentice or the receiver to generate the information based on them. So the transmitter now is not a transmitter, it's a teacher, because he takes, let's say, federated learning. He understands the main concepts, the meaning of the main concepts there, sends them over the channel, and he relies on the brain of the apprentice, the student, to actually fill in the gaps. I don't tell you everything today. I only tell you bits and pieces of the papers. And I know because you're intelligent agents, you can actually fill in the blanks. And this is what we want to do here. Now, of course, there are a lot of challenges here. The first one is I have a data, right? What is the meaning of it? Some people thought, okay, the meaning is just, some representation like features in an image, but that's not really meaning. For us, what we propose is to actually create a machine language based on the causal structure of the data itself. So what are the information content of the data, and how are these elements linked in a causal-based model? And this brings these pillars of semantic communication. So we need to be minimally in how we represent the data. We need to create a language based on these data structures. We need to also have this reasoning. I mean, I should be able to understand the causes, but also regenerate the information. We need new metrics. So if you're in information theory, this goes beyond information theory, and we need computing resources. So why is this beneficial? Because if I'm only sending the meaning, it is easier for the apprentice to recover the information. Like if I send you an English sentence, the sentence, how are you? If I have typos in that sentence, you actually can still understand it is how are you. While in the classical design, we send them as bits and we say that every bit should be correct. And that may be too strict in this case. If I reason at the semantic level, I'm more robust to the channel because now you can correct errors in an intelligent way. I also have AI nativeness because now AI is from the bottom up built there. I understand the context of the communication link from the data structure. I am minimalistic in the data transfer. And now the receiver is not a dumb passive receiver. It's actually a generative, intelligent reasoning-based device. So I'll show you some results and then conclude. I thought, had you told me I have 45 minutes, so I have a few more minutes to conclude. So this is a more complete. So we have a kind of a tutorial on this, but we also have a concrete recent work. So look at this end-to-end semantic communication model. Just focus on this part. These can be ignored. So we have a world state we want to perceive. We extract some attributes. Everything in white is something we don't control in this paper. And then we need to extract the information, the meaning. We do that by using generative flow networks that allow us to extract the state space inside the data, which is really causal variables. These are causal variables telling me how the data points are interrelated. And then these causal variables, ZI, I also represent them as ZT, so these two are the same. And then I need to send over the channel. To send over the channel, you can use, for example, one way to do it is to pick any value for Z of T. And this is what we call the syntactic space, which is all possible values for Z of T. Or you can say, well, I have this semantic space, but I can even make it smaller by using a language that is even smaller space, which we call the representation space. So can I create a smaller representation of the syntactic space? This is done with the purple bullet here using game theory. And then everything in pink is done with neural AI, meaning neural networks. Everything in green is done with symbolic AI, which means logic and deduction in some sense, which is why we call this Neuro-Symbolic. And then we have at the end, if you need that, that's not necessary. And then we do the extraction, finding the original data based on what the language has sent me. And then the device can do a logical formula like OR, XOR, and he can take an action, like a robot taking an action in the environment. And this can flow back to the device. So we showed that two things. This boils down to two problems: a language problem that we solve using game theory. This allows me to create the language based on my representation, and a causal reasoning problem that allows me to actually extract the causality from my system using a causal graph, a cyclic graph. And at the listener or the apprentice, we can evaluate logical formulas like, I can do this based on that. We solved these two problems, and I'm not going to go through the math today, but I can show you some proofs. For the language problem, we proved that if you're familiar with game theory, the game has three equilibria. Two of them are very trivial. One says everything you have, you send with one information representation, which makes no sense. The second one says, okay, everything is sent using everything, right? And that's also makes sense. But turns out there's a third equilibrium called partial pooling, which actually tells me that you can create a Voronoi tessellation of your representations of your syntactic space, and then do the representation, which is very interesting. So we can find you the subset here. We also proved that we can reduce the number of bits compared to a classical system based on a lot of, it's a very elaborate proof here. We also proved that the reliability is better as well. So we can also show that. Now, using simulations, we can show first that as you learn more tasks, so tasks 1, 2, 3, and 4 are sequential. Because I'm using generalizable AI, I can actually reduce the number of communication rounds needed. So I now understand my context, so I can learn faster. You can see the blue takes like 12 communication rounds. The pink needs 30. So you're getting better and better over time. We can show that our reliability is much better than any other existing state of the art, and there's very few actually in this. We also show that the number of physical bits that we transmit are smaller than these existing ones. And with this, I'm gonna conclude with what are we doing else other than this? We're looking, if you're in wireless, really pure wireless, we're looking quite a bit at, like terahertz bands, reconfigurable surfaces, digital twins, and metaverse of the wireless as well. Connected autonomy still plays a role in my group, even though lesser than in the past. Again, I talked about semantic, I talked about reliable learning. I have a group of students looking at networks and quantum networks and quantum AI. We have a MURI grant that's ending soon though, but it looks at age of information. And there are other things we're looking at: resilient infrastructure, game theory, and other things. So at the end, wireless and AI are converging into an integrated system. You have a lot of research problems you can look at. I gave you only a flavor of that. And you can see there's a need for collaboration between AI and systems researchers. And that's I think it's a great area for that. And finally, I'm happy to answer questions.
Thank you, Walid. It was a very insightful talk. The way to see the intersection of wireless systems and AI, it's very, exciting to me.